Welcome back to the Explainer. Today we're doing something really cool. We are initiating a full-scale geological scan of the planet. We're going to take a journey straight down into the blistering heat of Earth's interior and then follow the literal path of molten rock all the way up through the crust, onto the surface, and right into the clouds. It's this epic story of creation and destruction, totally driven by igneous processes and the towering giants we call volcanoes. Here's the game plan for our scan today. Magma origins, Bowen's reaction series, classifying igneous rocks, intrusive rock bodies, volcano types, and finally, volcanic hazards. Okay, let's dive right in. Section 1, Origins of Magma. So, starting our scan deep in the Earth, there's actually a pretty common misconception that the entire mantle is just this churning ocean of liquid rock. But in reality, it's mostly solid. For rock to turn into the liquid magma that fuels volcanoes, it has to cross a very specific temperature and pressure threshold called the solidus line. And there are three main ways this happens. Step 1 is decompression melting. This is when hot mantle rock rises, the confining pressure drops, and it just melts without the temperature even going up. Pretty wild, right? Step 2 is flux melting. This is where volatiles, things like water and carbon dioxide, get introduced, usually at subduction zones. That actually lowers the melting point of the rock. And step 3 is heat-induced melting, which is exactly what it sounds like. The ambient temperature just gets way too hot for the rock to stay solid. Moving right along to section 2, Bowen's reaction series. As our scan moves a bit higher, we find pools of newly formed magma that are starting to cool down. But here's the thing, it doesn't all freeze at once. Back in the early 1900s, a geologist named Norman Lell Bowen figured out that different minerals crystallize at wildly different temperatures. If you look at the high end of our scan, you've got mafic minerals. These are rich in iron and magnesium, like olivine. They start crystallizing out of the melt at scorching temperatures, right around 1250 degrees Celsius. But on the low end, you have felsic minerals, rich in silica, like quartz. These guys stay liquid much longer and only crystallize when the magma cools all the way down to about 700 degrees Celsius. Which brings us perfectly to Section 3, Classifying Igneous Rocks. That temperature-driven cooling sequence actually gives us the exact chemical recipe we need to classify rocks based on their composition. Check out the silica gradient here. Felsic rocks, like granite, are absolutely packed with silica, usually between 65 and 75%. Intermediate rocks sit right in the middle, while mafic rocks, like basalt, drop down to about 45 to 50% silica. And just off the chart, you've got ultramafic rocks from the deep mantle sitting below 40%. So why does this matter? Well, that specific silica percentage dictates exactly how sticky and viscous the lava will be when it finally erupts. And that is a real game changer, as we'll see in just a second. But first, we really have to talk about texture. Texture tells us the speed at which the rock cooled. As magma rises, the drop in pressure causes dissolved gases to just rapidly bubble out of the solution. The source text nails it by describing this as being like the fizz in an opened bottle of soda. If the rock cools fast enough, those gas bubbles get permanently trapped, creating what's called a vesicular texture. This gives us hole-filled rocks like scoria, or pumice. In fact, pumice is sometimes so light that it'll literally float on water. Okay, let's look at how this builds into a complete classification matrix. It's like a giant puzzle. On one axis, we have cooling speed, which gives us texture. So phaneritic, or coarse-grained, means it cooled slowly underground. Aphanetic, or fine-grained, means it cooled incredibly fast on the surface. On the other axis, we have our composition. So if you have a felsic rock that cools slowly underground, boom, you get granite. But if that exact same felsic magma erupts and cools quickly on the surface, you get rhyolite. Scanning further up, we hit Section 4, Intrusive Igneous Rock Bodies. Continuing our spatial journey upward, our sensors are picking up these massive, frozen structures hidden just beneath the Earth's surface. These are intrusive igneous rock bodies, basically the geological ghosts of ancient magma chambers. The absolutely crucial thing to remember here is the difference in how these rocks form and survive. Intrusive, or plutonic rocks, are trapped underground. Since they cool over thousands or even millions of years, they grow really large, durable crystals. Extrusive, or volcanic rocks, erupt right onto the surface, cooling so quickly they only form microscopic crystals, or they even shatter into volcanic glass, like obsidian. Because intrusive rocks have those larger, stronger crystals and aren't immediately subjected to surface weathering, they're way more likely to survive deep into geologic time. When this intrusive magma forces its way into the weaknesses of the native rock, it leaves behind some truly incredible formations. If it cuts vertically across existing rock layers, we call that a dike. If it squeezes horizontally between the layers, it's a sill. A laccolith is where magma creates this massive, blister-like bulge between sedimentary strata. And when giant underground magma chambers, called plutons, merge together, they form batholiths. To put that into perspective, the iconic granite peaks of Yosemite National Park in the Sierra Nevada batholith, that whole shebang is formed entirely from these massive, slow-cooled, intrusive bodies that erosion finally exposed over time. But what about the magma that doesn't stay trapped? Our scanner is right at the edge of the crust now, tracking a plume of molten rock moving rapidly toward the surface. The pressure is really building. The structural integrity of the crust is failing. So what exactly happens when this fiery engine finally breaks through? Well, real quick terminology shift first. The very second that molten material breaches the surface and touches the air or the ocean, it drops the title of magma and officially becomes lava. And that takes us right into Section 5, volcano types and eruptions. Now, you might be wondering, how does the microscopic chemistry we talked about earlier translate into massive mountain topographies? It's all about that silica. On the left, you've got a shield volcano, like the ones in Hawaii. These are formed by mafic lava, which is low in silica. Because the silica is low, the lava has a really low viscosity. It flows super easily, almost like hot syrup. This creates massive, broad, gently sloping mountains through very predictable, effusive eruptions. But on the right, we have stratovolcanoes, like Mount Fuji. These are fueled by felsic or intermediate lava, which is high in silica. That makes the lava incredibly viscous and sticky. Think of it more like toothpaste. It doesn't flow easily at all, so it just piles up, trapping volatile gases until the pressure causes a violently explosive eruption. And that's what creates that classic, dangerously steep, cone-shaped mountain. Our scan is also picking up a few other fascinating eruption styles. There are calderas, which are these massive craters left behind when a volcano explosively empties its magma chamber and just collapses in on itself. Crater Lake in Oregon is a great example. You have prehistoric flood basalts that literally paved entire landscapes in lava. And then there are cinder cones. These are steep, short-lived volcanoes built entirely from ejected cinders. Actually, there's a crazy dramatic example of this. Back in 1943, near the village of Periquetin in Mexico, a cinder cone violently burst out of a farmer's flat field, out of nowhere. It shot cinders and ash into the sky, and within just 8 months, it had built a cone 1,200 feet high, eventually pouring out lava that completely destroyed a nearby town. Now we're shifting the HUD to Emergency Red, Section 6, Volcanic Hazards and Risks. Surveying the aftermath of these explosive events, it's pretty clear. Volcanoes are majestic, for sure, but they are incredibly deadly. And the primary hazards extend way beyond just slow-moving lava. Volcanic gases, for instance, like carbon dioxide and sulfur dioxide, are invisible killers. They can silently sink into low-lying basins and just suffocate everything there. Then you have lahars. If an eruption melts a mountain's glacier or snowpack, that water mixes with volcanic ash to create a lahar. Picture this as a rapidly moving slurry that behaves exactly like wet concrete, just racing down the mountain and burying absolutely everything in its path. But the most terrifying threat of all, the pyroclastic flow. When a steep composite volcano violently erupts, it can send a turbulent, cascading cloud of hot ash, gas, and huge lava blocks racing down its flanks. Listen, this isn't just a smoke cloud. It is a hyperheated avalanche exceeding 700 degrees Celsius, moving at speeds up to 120 miles per hour. To put it bluntly, there is absolutely no way you can outrun it. So, as we wrap up our scan from the Earth's core all the way to the clouds, we are left with a pretty stark reality. Volcanoes are the ultimate world builders, literally forging the ground beneath our feet through the beautiful logic of Bowen's reaction series and igneous cooling. But they're also relentless destroyers. As human populations keep expanding closer and closer to these sleeping giants, it really begs the question, how will our modern, growing cities adapt and survive while living right on the edge of the blast zone? Thank you so much for joining me on this explainer. I really hope it sparked your curiosity to dig deeper into the incredible fiery engine running right beneath our feet.